Okay, I used the coffee break also to do a little calculation about the inverse of the matrix, right? I usually, oh sorry, yeah, screen. So what I usually do I use a symbolic toolbox and then I write the matrix and do that stuff. So finally, I found the answer that's more important. So now I've written down what the inverse of that matrix is, right? With the 1 over cosine, I dropped the minus sign that's incorporated in here. And then we see, well, oh yeah, it's nice. It's again at the most double products of sine and cosine, but we have this singularity at y is 0. And now I want to focus on that. So what is going on? So again, to understand what is going on there, we have to draw a picture. So let's, and since it's already in the initial configuration, we are in trouble. So let's draw that initial configuration. 3 axes, x, y, and z. First rotation about this, second rotation about this angle, and then the third rotation about this angle. And so apparently we have here this omega, let's say what is phi, right? We have here this omega theta, because it was the theta axis and this was the psi. And here we have this omega psi. Now, in this initial configuration, it's super clear that if we have some angular speed, and I just draw a vector here, omega, then the relation which we write down here of omega versus phi dot, psi dot, we can easily write it out because, well, we know this vector, we know this one, and we know everything is 0. So if everything is 0, how does this matrix look? Then we have 0, 1, 0, 0, 0, 0, 1, 0, 1. Yeah, so remember that. I hope I remembered it well. So we get omega x, omega y, omega z equals 0, 1, 0, 0, 0, 0, 0, 1, 0 times psi dot, theta dot, and phi dot. And now, so this is in the 0 configuration, 0, 0, 0. That's all what the angles are. So that's the phi, theta, psi. Okay. Now looking at this matrix and looking at the figure, I know what is going on. Because if we want to write the inverse of this one, phi dot, theta dot, psi dot is something with the omegas, omega x, omega y, omega z, we see that it's sheer impossible, for instance, for these omegas to have a contribution which is outside this xz plane. If omega has a y contribution, we cannot describe that with these omega vectors because they are all 3 in the same plane. And that's expressed by this matrix by saying, oh, omega y is all zeros times this. So we cannot resolve omega y. We don't know how to do that. There is no way. You cannot do that in this configuration. We can say what the phi dot is directly from the omega, but here it says, oh yeah, the omega z is the sum of these two. And since we have no rule here for how do they depend on each other, then yeah, there is no way to say what is phi dot and what is psi dot, because the sum of these two is the omega z, but what they are individually we don't know, and we cannot express the omega z. So that is a physical interpretation of this singularity. There's a word which goes by that, and we call it Gimbal lock. Now, why do we call it Gimbal lock? Well, to make such a sequence of rotations, you usually use gimbals. That's a circular thing with two bearings, and then again you mount a circular thing with 2 bearings, and a circular thing with 2 bearings. And then you can have a rotation about one axis, about the other axis, whatever. And with those 3 gimbals, you can build a thing. I find it always very confusing. People use gimbals to have the center always at the same point. I love this Kenshin series. Because with this Kenshin series, it's super clear that all rotations is in this plane, all these rotational speeds. So if you want to resolve that, then you have to make sure that no 2 axes are aligned. And you can do that very easily. You can, for instance, reformulate. Reformulate. You can say, well, instead of this starting from this configuration, I can say, well, I flip one of these. So I say, well, I start with my orientation like this, and like this, right? Nice perpendicular in 3 directions. So this would be Euler angles. So if this is x, y, z, then this would be an Euler angle which starts with z, then we get x, and then we get y. And they say, oh yeah, solved, everything is solved. Well, what happens when you run this problem, then somewhere you get the case that this middle angle, so let's call them alpha, beta, and this one gamma, somewhere in your analysis beta will approach 90 degrees, plus or minus. And then what happens? Well, then again we are in the same horrible situation. Then we have this, right? Then axes are aligned again, and we have gimbal lock. Ta 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 ta. So whatever you do, whatever set of Euler angles you think of, and how many Euler angles are there actually? How many different Euler angles? What did we see now? We started with x, z, x. Now I showed a z, x, y. How many do we have? 6, 9, 12. No idea? Because? Why 3k times 2k1 times 1? No, it's almost right. So how does it go? The first one we can take any axis. So we have 3, right? You can add the x, y, z. Then the second rotation cannot be the same in the same direction, because then you have 2 hinges always in series. So for the second rotation, if you choose x, it should be y, z, or and vice versa. So you have 2 choices. The third rotation, again you have 2 choices, as long as it's not that original one. So 3 times 2 times 2 makes 12. You have 12 different sets of Euler angles. Yep. Okay. But there was a sideline, so back to this. Whatever you take, whatever set you take, say for instance, some say, oh no, I like x, y, z, that's nice. No, whatever set you do, you always will run up that the middle one will be such that the 2 other axes will be aligned. Always. So that is a big disadvantage of these Euler angles. In mathematical terms, it's called SO3, these rotational mappings in the 3-dimensional world. And SO3 has this problem. Mathematicians know about this. I don't understand what they all mean with that. But there is a way to solve it. And the way is very obvious. Instead of using those 3 unique parameters, where it turns out to be impossible to find 3 unique parameters, 3 Euler angles which do the job, we use 4 parameters. You can use axis angle, or you can use 4 Euler parameters, of course Euler parameters, because Euler also discovered this singularity problem. It used to be a topic of the course. I'm not going to talk about it now. It's in the book. If you're ever going to do this real rotational thing with all kind of rotations, Euler parameters are very useful. And since we know how to work with constraints in our mechanical system, it's super easy to say, well, then we take 4 parameters plus 1 constraint. We can work with that. Okay. So Then finally I want to talk about how do we now formulate our equations of motion, right? So I talked about Gimbal lock, about Euler angles being coming into the singular configuration. You can reformulate to get rid of that, but you will run into it again. How does the calculation of some 3D rigid body system with constraints, how does it work? Well, let's do an example to see what we all need to do a calculation. And as an example, I look at some apparatus. There was a very nice name for it, but I forgot. It's a turntable. Starts with a turntable, and of course the turntable is able to turn, and then mounted on that turntable are two rotational hinges, one here and one here. So they're mounted on the table, and they operate some pendulum. So, and here's then the center of mass of the pendulum, and here is the, how do I draw that? Center of mass of the disk. And this is inertial space. Yeah, so here we have some inertial coordinate system. X, Y, and Z. This is inertial. And this is then body 1, and this is then body 2. Did I put names with it? Yeah, the first rotation I call alpha, and then this is beta, and this was gamma. Yeah, makes sense. So can you imagine how it works? This turntable turns, and then this pendulum can move in this direction, and it can move like that. You would think, oh, it can move in any direction. No, these two hinges in series, they constrain one rotation, right? It's not like a ball and socket joint here, because the thing cannot rotate about its own axis. Yeah? This apparatus is used for studying balance of a stick. So if you want to do balancing on a stick, then and you do it on a cart, then the cart will move to infinity left and right. And that is a bit difficult to build that apparatus. So you make it on a circle. So then the thing flips upright, and then you move the turntable to balance, and you see what control algorithms can I use to balance. And so you have an infinite long cart, actually. And there was a nice name. Yeah, the Fujikami pendulum or something. I don't know what exactly the name was. Anyway, nice 3D rigid bodies with constraints. Now, whatever approach we take, we have to formulate our equations of motion. And we can do DAE approach. We can do, so for our equation of motion, there are a number of routes. We can differential equations with constraints, algebraic constraints. We can, Lagrange, some love Lagrange equations, we can do that. Or you can do TMT method. As you like it. Talking like Shakespeare, as you like it. But for whatever approach we do, we have to take our basic Newton-Euler equation and cast them into the form we want, right? So what are our basic equation? So the basis is Newton-Euler for all the bodies. And for the rest, plus the book we have. Because in our book we have all kind of formalisms to make those equations of motion. Now, whatever formalism you take, remember that it always started with virtual power. Right? So, how I gonna formulate the equation of motion is irrelevant. I have to start with a thing called virtual power. So I have to say, the virtual power of the system. So I have to sum over all the bodies. So the B is all the bodies. And what do I have to sum over the bodies? Well, I have to sum the Newtonian, the virtual Newtonian equations plus the virtual Euler equations, right? That's how it works. So again, I sum over the bodies. Now the Newton equations, I know. The forces at the center of mass minus some mass matrix times the acceleration. And then it was virtual power, so it was times this one. And some transpose, because I'm now working with vectors and matrices. Yeah. So this is Newton part, right? Super easy. And since I do the whole system, I add them all up. That's what the index B is. Okay, now let's add the Euler part. So the Euler part is, yeah, again, Euler equation of motion, right? So we have the sum of the torques, and then equals, in my head I say then sum of the torque equals mass moment of inertia, angular rate, yeah, plus omega cross IB omega. Yeah, and that should do the trick. Close that bracket, close this one, times the virtual angular velocities, angular velocities. And yeah, we can put big brackets around this. This is the whole thing. Now, remember that this mass moment of inertia matrix changes when the thing changes orientation. If we express it in the space fixed frame, it's a bit cumbersome. So we like to express everything in a body fixed frame, because then these guys are constant. That simplifies our work a lot. So what do we need? Well, we need then expressions for our virtual velocities and acceleration of the CM, and for our virtual angular speeds and our angular accelerations. Okay, so let's start with the Newton part. Oh. Let's start with the Newton part. So we need expressions for our positions, xb. Now, let's say we do, shall we do TMT method? Yeah. What do we do then? Well, then we find a mapping for every body which maps our generalized degrees of freedom to our coordinates, right? And in our case, if we would do TMT method here, then what would be our q's? The q's in our example would be alpha, beta, gamma, right? So this you have to write out. For this body, well, here it's super simple. It's stationary, so you can even leave out those coordinates. But here, the position of this point, well, it's a function of alpha and maybe some dimensions here, r, and here's also a dimension d over 2 or something like that. And given what those dimensions and the angles are, you can write down what the position is. That's doable. It's work, but it's doable. And then we can say, oh, the velocities, yeah, that is, I have to differentiate this one. And virtual velocities, well, that was just putting this magic symbol there. Nothing much changes. So virtual velocities. So I've now covered this. Yeah, so this we know. I still haven't got the accelerations. Oh, differentiate again. Q double dot. And then we get all these complex convective terms. Differentiate twice. Q dot. And I have a tendency, because this is just a vector, it shrinks down to just a vector with those three components. So I have a tendency to write that down as h, some vector h of b. Complex, and it's state dependent, it's not very interesting. Okay, so that was the Newton part, everything covered there, right? You can plug in everything and multiply out, and you get reduced mass matrices and right-hand side terms where this all comes. It's all in the book. So what do we need for the Euler part? Well, for the Euler part, we need, looking at the equation, we need the angular velocities, right? And so we need the angular velocities of the body, yeah, expressed in terms of our degrees of freedom and the speeds of our degrees of freedom. So these omega b are a function of q and q dot, because we're talking speeds here. Okay. But we know more because we know that although in the generalized coordinates it can be cosines and sines or quadratic or any mathematical function. But in the speeds we know it must be linear. Angular velocity must be linear in the time derivative of our parameters. Otherwise there's something wrong. So this should be something like, and I call it a matrix B here, B of that body, which is a function of generalized coordinates, but times the speed. So it's always linear in those q dots, this thing. Therefore I separate them, I know. And remember where we wrote down our Euler angle time derivatives versus our angular speed, that was something here, and it's always a linear expression. And we can do that for these bodies. Very simple. I will come to that in a second. So let's assume we can do that. Well, we can already look a little bit at it. So what do I need? So my q's here, my generalized degrees of freedom, are independent even alpha, beta, and gamma are this. So if I want to write down what the angular speed of this thing is, well, here I have an angular speed of this table, and then I have two angular speeds here about these two axes, and the three together result in the angular speed of this body with relation to that inertial frame. And I have to always express for Newton order always with respect to some inertial frame. That's how the equations work. So three angular speeds in series. So again, something like I did in before the break, but here different. Now, what do we need for these Euler equations? Well, we need this omega. Then we need the virtual angular velocities. Well, again, that is super simple. That's just B, and I repeat of Q times delta Q dot. Just put a virtual in front of it. And here I need, of course, the angular accelerations. So I need to differentiate this, and I get omega dot prime of B is, I first keep the B constant, BB times Q double dot, plus, and then I get what we call these convective terms, Q dot, and again I have a symbol for this, and I call it G. A bit confusing, but GB. Okay, so now I have all my elements. So I can substitute everything into our virtual power. So substitute all in delta P. And then for all virtual velocities of the body and all virtual angular, it's already speeds of the body, I get my equations of motion. As many as there are degrees of freedom. So how does it work? Well, finally I get something like this, sum over the bodies, big bracket. I get all these transformation matrices, TBQ transpose MB TBQ, right? So that is for the Newton part. But I also have, of course, my Euler part, and then I get my BB transpose times my inertial stuff times BB. Close the bracket, and I get Q double dot. So this is my reduced mass matrix, reduced on the terms of my degrees of freedom. The part of the linear part and the orientational part. And then on the right hand side, well, of course I have my generalized forces, which are dual to those generalized degrees of freedom, plus, and then I get again a sum over all the bodies, and then I get the right hand side of this guy and the right hand side of that guy. And the right hand side of this guy is again this TBQ transpose times the forces minus MB, and then these convective terms, remember? And then the rotational part is this BB transpose times, well, this is the torques applied. Then again, I get my, likewise here with these convective terms, which I call GB. But since it's Euler, I also have this minus omega prime b cross I prime b omega b. And these convective terms which are inherent to the Euler equations. Close this bracket and close the square bracket. Okay, and you can say then this compromises to some m bar, q double dot is q bar. Still very Newtonian, mass times acceleration is forces, but then on the reduced coordinate basis. Now finally, and that is the connection with today's lecture, this first part we all did in all the homework assignments, right? Now we have to focus on this part, this rotational part. And as you can see, forming these are easy as long as you have this BB, and then you can find the transpose, and if you have these convective terms. So for the rotational part, it breaks down to formulating this expression. Yeah?
How can we calculate that matrix B? How can we calculate that matrix B?
So the whole problem here is to formulate the matrix B. That was the question. How do we find B? That is the problem here. And for that we go just to our sketch, to our problem. And we sketch that again. So we have our turntable here. I have my hinge here. I need a coordinate system, of course. Yeah. Hopla. And then we had this hinge here and this hinge here. And then we have our body here. Hopla. Yo. Okay. Now we want to focus on this angular speed in the body fixed frame versus our Q and Q dot, right? Q dot, that's not a Q dot. Q dot. So how do we do that? Well, looking at the picture, this is the inertial frame with the X, Y, and Z. This was alpha, right? And this is glued to the inertial world. This is my body world. And and then I just have to draw these angular speeds there. So this is an angular speed, omega alpha. This is an angular speed, right? Vector. This is omega beta. That's the beta axis. And this is the gamma axis. And then here we have perpendicular this omega gamma. Yep. What else do we need? That looks about right. So now we can form our omega of body 2. So this is body 2. And I want to express it in the body fixed frame, right? That's the thing I want. How do I do that? Well, let's first drop that we put it in a frame. I say omega 2. I know for sure that it's omega alpha plus omega beta plus omega c. Because after this series of hinges, you end up at this body. And rotational vectors, every part of a body has the same rotation. That vector you can replace in space, as long as it keeps the value, the direction and the magnitude, and you can put it on any side. So the sum of these three angular rotational speeds is the rotational speed of this body. So that's what we say here. Now we want to work in components, so we want to know it in the body fixed frame. Omega 2, which is actually this omega prime of 2. Okay, well, let's start with the most easy one, which is already in the body fixed frame. Yeah, the gamma, Oh, I didn't write gamma here, sorry. Omega gamma. So whatever happens, I have here already omega gamma, and that is, what is the omega gamma? That's about minus x-axis. Oh, strange coordinate system. So minus gamma dot 0, 0, right? Okay, then omega b. Well, that's almost in the coordinate system, but there is this gamma, so it's almost there. So in this coordinate system, it's in the y-axis, so that's 0 beta dot should be a dot 0. Then, but we have to transform it to this body, and that's the inverse transformation. Yeah, and the inverse transformation. Well, not about the beta, but the gamma, of course, because that changes the orientation of the body, this gamma, right, this x. So we need here, this is a plus, r gamma, but then transpose, because we have to go back to our body. You could also write, it's the r of the minus gamma. If you look at these matrices, it's identical. The r of minus gamma is identical to r gamma transpose. Then finally, the first one, this one, well, there are apparently two transformations. So it's about the z-axis, 0, 0, alpha dot. And then I have the beta axis and the gamma axis. So I have r beta transpose and r gamma transpose. And that should do the trick. Now I have, and that should answer your question. So now I have my expression of my omega 2 prime is some matrix times, and now watch again how I'm going to write alpha dot beta dot gamma dot. So watch the order, and compare it to here. Here I use the order to really donate angular velocities, but here I use just as an ordered pair. And then we have here these 9 entries, and they shouldn't be so difficult. Okay, I think this sort of finalized my lecture for today and for the whole course. There will be office hours in the week of the exam, so on Wednesday, the Wednesday before the exam, that is 543, but I'll put it on the website, so then you can have last minute questions for the exam. Yeah, okay, it was my pleasure. See you all July 5, sorry.